Binding energy and mass defect. The total mass of a nucleus is always less than the sum of its constituent neutrons and protons. So where has this mass gone? It has become energy, such as radiation or kinetic energy. In other words, when a nucleus is put together, you've got a certain mass of neutrons and protons, you put it together, energy is released, because the mass of the combined protons and neutrons in the nucleus is less. Where did that mass go? It had to go somewhere because of the conservation of mass energy. In this case, it goes to energy. So we have a definition here. The total binding energy, remember we just talked about putting a nucleus together, so the difference between the total mass of the individual nucleons, the individual protons and neutrons, and the final mass of the nucleus is called the total binding energy of the nucleus. In energy units, the total binding energy is given by E sub B for binding energy, delta M, where this delta M is the mass difference, times C squared. In words, the binding energy is the amount of energy needed to be put into the nucleus in order to break it apart into protons and neutrons. Let's show an example as to how to calculate the binding energy of an isotope. We're going to start with boron 10. And notice I just say boron 10 because the 5 here, which tells you how many protons there are, only boron has 5 protons, so that's somewhat redundant. We have 5 protons, 5 electrons, and 5 neutrons. Now, for our calculations, we're going to use the mass of the hydrogen atom for every proton we have, because when we're subtracting out the mass of the boron isotope, that includes all the electrons, and even if they're small, it is a factor. So we will be using the hydrogen atom when we talk about how many protons we have. That'll become clearer hopefully as we do the problem. So the total mass here, we have 5 neutrons. They have an atomic mass unit. Each neutron weighs or has a mass of 1.008665 atomic mass units. The hydrogen atom, which is a proton plus the electron, is 1.007825 atomic mass units, and we have 5 of them. And the mass of boron, which includes 5 neutrons, 5 protons, and 5 electrons. So you can see by using the hydrogen atom, we will subtract out the electrons so they won't come into the problem. So we will find the mass defect. We have over here, here's the 5 neutrons. You can see 5 times the mass of the individual neutron. We have here the hydrogen atom, which includes the proton and the electron. And then here's boron, and there's just one of them. And again, this has 5 neutrons, 5 protons, and 5 electrons. And we get a mass defect of 0.069513 atomic mass units. So that shows that the individual constituents that made up this isotope have a greater mass than the boron isotope. So where did that mass go? And that will be shown on the next slide. The neutrons and the protons weigh more than the nucleus that is put together from them. And that missing mass is converted into energy, which is the binding energy. So the binding energy is either how much energy you need to break it apart, or it's how much energy which is released when you put the neutrons and protons together to make a nucleus. So we need to convert the mass defect that we found on the previous slide to either kilograms or this other unit. Now we're going to see why this sometimes is more convenient to use, and certainly for nuclear physics it's more convenient to use. We have, this is how many kilograms there are per atomic mass unit, and then we have 931.5 MeV divided by C squared per atomic mass unit. So we have 2 mass defects here. One is in kilograms, one is in this other slightly more unusual unit. We then find the binding energy from Einstein's formula, E equals mc squared. So we substitute in, if we want to find the energy in joules, we use this term here, the kilograms, times the speed of light squared, and we get 1.0388 times 10 to the minus 11th joules. If we want it in MeV, we take this mass defect, and you can see the math is quite a bit easier. We have MeV per c squared times c squared. These guys just cancel each other out. and we're left with a binding energy of 64.75 MeV. So the math is easier, and it's a little easier to say when you're working with nuclear binding energies than worrying about joules and kilograms.